Hello everyone, let's get started. Today we are going to dive into our core topic under deep learning architectures, the pooling layer. We will explore how this specific layer manages spatial dimensions and optimizes data flow within a network. Let's establish our baseline definition. A pooling layer is used to reduce the spatial dimensions, specifically the width and the height, of feature maps while systematically keeping the most important information. This operation reduces the size of feature maps through down sampling by applying a small filter over each region of the feature map and summarizing the values within that region. This process helps reduce computation and control overfitting. When we look at the core purposes of this architecture, it serves several vital functions. It helps to reduce computation, reduce memory usage, and prevent overfitting. By doing so, it forces the neural network to focus on the most important features across our data layers. In modern neural networks, there are a few primary variations of this operation. The most common pooling operations are max pooling, which selects the maximum value from a region, and average pooling, which computes the average value within that region. To properly build and architect our networks, we must understand how spatial dimensions shift. Please refer to the formula of the output size for a pooling layer displayed on the screen to see how the output height and width map out alongside the channel count. In certain network setups, padding is introduced around the boundaries of our feature maps to preserve edge information. When padding is applied to the input, please refer to the modified formula with padding displayed here on the slide. Let's ground this theory in a quick introductory scenario. For an input feature map with a filter size and a stride length, please refer to the calculation on the screen to see how the mathematical output simplifies cleanly. This structural behavior means our feature maps change size systematically. As a result of this calculation, please refer to the output dimensions on the slide, noting that the channels remain exactly the same. Straight to the main office right now. Now let's examine a more generalized mathematical layout for a typical feature map layer. Suppose our input feature map has dimensions representing the input height, input width, and number of channels. To track the exact structural transformations of these generalized dimensions after the pooling operation takes place, please refer to the box formula highlighted at the bottom of the slide. Is highlighted at the bottom of the bottom of the slide. To track the exact structural transformations of these generalized dimensions after the pooling operation takes place, please refer to the box formula highlighted at the bottom of the slide. Now let's highlight an absolute rule of pooling layers that you must remember. Pooling does not change the number of channels under any circumstance. Only the height changes and the width changes, while the channels remain completely the same. Let's verify this rule with a practical example. For our input dimensions, the output changes spatially, but please refer to the notice on the slide showing that the channels remain exactly the same. Let's walk through a complete problem to see how the internal steps resolve. In this scenario, we start with an input height, a pooling filter size, and a stride length. Please refer to the output height equation on the screen to follow our initial setup of We evaluate this equation by working through it sequentially. Please refer to the calculation of steps 1 and 2 on the slide to see how these initial arithmetic steps resolve. Because our dimensions match, the calculation follows the exact same path for the width. Please refer to the final output vector on the screen to see our resulting spatial layout structure. Let's tackle another explicit case to solidify this workflow. In example 1, we are handed an input feature map with a specific height, width, and channel count alongside our pooling filter and stride length parameters. When we process these specific dimensions through our framework, we evaluate the height, width, and channels systematically. Please refer to the calculation steps on the screen to see how they map directly to our final output vector. To summarize why these layers are so vital, pooling layers play a key role in making networks efficient and robust by simplifying feature maps while preserving important information. It reduces dimensions, leading to faster computation and fewer parameters. It provides translation invariance so small shifts do not affect the output, helps control overfitting, improves generalization, and supports hierarchical learning. A classic example is making sure a slightly shifted object, such as a cat, is still recognized accurately by the network. Let's look closer at our specific types of pooling operations. First, max pooling selects the maximum value from each region to capture prominent features like edges and textures. Please refer to the picture of max pooling on the screen to see how this extraction works. Second, average pooling computes the mean value within each region to capture overall feature information, producing smoother feature maps. Please refer to the picture of average pooling to see the contrast. Finally, global pooling reduces each channel to a single value. Thank you all for your attention today.